Okay, so today we've reached the last lesson of this part of Chapter 5. So remember, we're splitting Chapter 5 up into two separate subunits, and this today is the end of that first part. And we're going to be looking at curve fitting with quadratic models. So there is a warm-up here, and it says to use matrices to solve each system of equations. So before I set you on your way with the warm-up, I just want to remind you that when you use a system to solve a set of equations or system of equations, when you use matrices, you have to create what's called a matrix equation. So our matrix equation is comprised of a coefficient matrix, a variable matrix where you list your two variables. So for instance, in example 1 it would be A and B, but you could just think of it as X or Y, or X and Y or something like that. And then you have a constant matrix, and in this case, and in fact I'll actually help you get the coefficient matrix set up also. So the coefficient matrix for this one would be 3, 1, to -6. And remember, in our calculator we call that A. When we set that up in the matrix menu, we set that up as A. And then we call the constant matrix B, which is -5, 30. And then to solve, this is what we do. We solve by multiplying the inverse of A. So we just type in A and hit the inverse key, and then times B. And that should give us our solution for this system in the form of A and then B. So the first entry in that matrix will be whatever the A is, and the second one will be whatever the B is. So go ahead and pause the video now and solve questions 1 and 2 of the warm-up using matrix multiplication as a way of solving the system. Okay, so thanks for trying the warm-up. Take a look at the answers for questions 1 and 2. Question 1, the solution, the ordered pair would be 0, -5, and you could either write it like this or in ordered pair form. And for number 2, it would be 1, 5. And again, you could write it as a matrix, or you could write it as an ordered pair. So let's go ahead and take a look at our learning goals for today. So our first learning goal today is to determine if data is quadratic. So we're going to take a look at some data that's displayed in tables, and we're going to check to see if it's actually quadratic data. The second learning goal is we're going to use quadratic functions to model data. So much like we did earlier on in Algebra 2A when we took linear data and we used that data to write a linear model, we're going to do that same thing but with quadratic data. So we'll write some kind of quadratic function to model data. And we'll do this algebraically with matrices and also performing regressions with a graphing calculator. So we will be utilizing our graphing calculator here, and we'll be utilizing it using regression function and also using matrices. And then finally we'll be using quadratic models to analyze and predict. So we'll actually take this information, use it in some kind of real life situation to analyze the situation and to make predictions. Okay, so you may remember when we studied data to see if it was linear. And when we wanted to see if a set of data was linear, we had to first of all see if the inputs or the x values were evenly spaced, and then if they were, we looked to see if the first difference between the y values were evenly spaced, if they were consistent or constant. So for a set of ordered pairs to be quadratic data, well, what has to be the case? For a set of ordered pairs with evenly spaced x values, a quadratic function has a constant non-zero second difference. So instead of being first differences being the same, now we're going to be looking at the second differences. And we're going to go ahead and take a look at that in the context of this table that's given. So I actually have a set of, that this is data is quadratic. In fact, it's the ordered pairs for the function f of x is equal to x squared. And the x values, the inputs, you can see are evenly spaced. So we're going up by 1 each time. So -3, -2, -1, 0, 1, 2, 3. So that first thing off our checklist has been taken care of. We saw that the x's were evenly spaced. And now we take a look at the y's. So if we look at the first differences, so these are the first differences, we see that from 9 to 4 it's going down by 5. Then from 4 to 1 it's going down by 3. And then from 1 to 0 it's going down 1. And then from 0 up to 1 we're going up 1. From 1 to 4 we're going up 3. And then from 4 to 9 we're going up 5. So there's not a constant first difference, but there certainly is some kind of pattern going on here because the change was -5, then -3, then -1, then +1, then 3, then 5. And so now at this point we're going to check to see if the second differences are the same. And so when we do the second differences, we actually just use those new numbers that we just created, that first set of differences, and we see what is the difference between those differences. And so I can see from -5 up to -3, I went up 2. And then up 2 again. And then from -1 up to +1, we went up 2. And then from 1 to 3, we went up 2. And then from 3 to 5, we went up 2. And so you can see that the second differences are the same. And what that means is this is quadratic data. So let's go ahead and turn the page. So these next 3 examples ask us to analyze the data and see if it represents a quadratic function. So we're going to do exactly what we just did in that last example. We're going to first look and see, are the x values evenly spaced? So that's a really important piece of this too. If they're not evenly spaced, we really can't analyze the data. So you can see in example A that the data, the x values, are evenly spaced. They're actually going up each time by 2. So that's the first thing we have to check off our list. If they're not evenly spaced, we're not really even going to be able to tell this way what kind of data we have. So we just kind of check that off the list. And now we're going to go ahead and take a look at the first differences, because you can't check the second differences until you check the first differences. So we're going to see if maybe it might be linear. So the first y value is -1. Going up to 1, it's increasing by 2, then increasing by 6, and then increasing by 10, and then increasing by 14. So we know for sure it's not linear. I know that because linear would produce first differences that are constant. And so now we can go ahead and check the next level and see if maybe it's quadratic. So we'll see what's happening here. So from 2 to 6 it's going up by 4, then up by 4, and then from 10 to 14 up by 4. And right there, that tells me that this must be quadratic because the second differences are constant. Okay, so if you got that, we're at the point where we're going to have a couple U-tries. So we'll make B and C U-try questions. So do exactly what we just did in the last 2 examples and check to see if this data would qualify to be a quadratic set of data, if it would be a quadratic function. So go ahead and pause the video now and take a look at B and C and tune back in when you're done. Okay, so I hope you weren't too disappointed that neither of these sets of data were quadratic. In example B, though, you might have noticed that there was actually something interesting going on. The first differences and the second differences were not constant, so it was not linear or quadratic. But if you look at those output values, they look like they were, and in fact they were, each time being multiplied by a factor of 3. So if you remember back in chapter 12, we talked about that. That means this is sort of like exponential data. And then in example C, this turned out to be linear, so we didn't have to go past the that the first differences, because once the first differences are constant, that means this is linear data. Now, this brings up a common mistake. What a lot of people will do is they so want this data to be quadratic that they'll get the first set of differences, and it's the same. In this case, they were all +2, and then they say, oh, well, if we look at the difference between those numbers, it's all 0. Well, that should be that indication. If your constant difference is 0, that means that it's not that type of function. It's not quadratic. So it has to be something other than 0 for it to be quadratic. So once you get a constant difference at that level, at the linear level, at the first differences, you just stop there and you say the data's linear. It would best be represented with a line. Now, speaking of lines, when we wanted to write an equation for a line, we could accomplish that being given just as little as 2 ordered pair on that line. So just as 2 points to find a linear function, actually 3 non-collinear points define a quadratic function. So if we wanted to be able to write a quadratic function, we'd have to know at least 3 ordered pair that lie on the curve that's the parabola. You need 2 points for a line. You need 3 non-collinear, so they're not going to lie on a line anyway if they're on a parabola. They're going to be on a curve. So 3 non-collinear points will define a quadratic function. And you can find 3 coefficients, A, B, and C, of the standard form of a quadratic equation by using a system of 3 equations, 1 for each point. So if we have these 3 unknowns, A, B, and C, because we want to write an equation for quadratic in standard form, we'd need to have 3 equations. And each one of these equations would represent one of those points. And so if we could then create a system out of that, we could solve it to find out what A, B, and C are, similar to how we found out A and B in the warm-up with the 2 equations and 2 variables. Now we'll have 3 equations and 3 variables, and we'll use a system of equations to find those values so that we can write a quadratic function. Let's turn the page and take a look at that. All right, so we want to write a quadratic function that fits the points 1, -5, 3, 5, and 4, 16. So we're going to use each point to write a system of equations to find A, B, and C. So we'll take each point, we'll write an equation from it, and then that way we'll have 3 separate equations that we can write a system to solve for that. So what we do is we take that standard form of a quadratic, f of x is equal to ax squared plus bx plus c, and we plug each of the ordered pairs in to that function. So like the x, in this case the 1, -5, would go in both places where x appears, and the y will go in for f of x. So this is what that would look like if I substituted in 1 for x and -5 for y. So if I were to simplify that and then put the coefficients first and put the variables second, which is normally how we do that, it would look like this. 1a, because 1 squared is 1, plus 1b plus c, or 1c, because there's not a number in front of c, we say the coefficient is 1, would equal -5. Now I'm going to do the same thing with the next ordered pair. So this time I have x is 3 and y is 5, so I put the 5 in for y, or f of x. I'm going to put the 3 in for x. And so when I simplify that, 3 squared is 9, so that's 9 times a, or 9a, plus 3 times b, which is 3b, plus 1c, is equal to 5. Okay, so we're on our way. We've got 2 equations in 3 variables. We need 1 more. So now we put the 4 in for x and the 16 in for y. So it'll look like this. 16 equals a times 4 squared plus b times 4 plus c. So we're just plugging 4 in for x into that standard form. And when we simplify it, 4 squared is 16, so that's 16a plus 4b plus 1c and that's got to be equal to the y value, which is 16. So I've got my 3 equations and 3 variables. All I have to do now is translate that into a matrix equation and then use my calculator to solve that. So this is what the coefficient matrix would look like. The first line would be 1, 1, 1. The next line would be 9, 3, 1. And that final line would be 16, 4, 1. So that's just simply taking these coefficients here and putting them into a matrix, with the A's coming first, the B's second, and the C's third, and that's why our variable matrix is ABC. Now the constant matrix comes from over here, and those values create my constant matrix: -5, 5, 16, and if we set up so that this is called A, our coefficient matrix is A, and our constant matrix is B, we can solve this by multiplying the inverse of A, so A inverse times B. So I'm going to add a little calculator video tutorial in here, so in case you need a little refresher on how to input matrices, how to solve matrix equations on the calculator. And so then if you had trouble with the warm-up and doing the warm-up, once I go through this little tutorial, you could always go back and complete that warm-up and practice a little more with that warm-up. So I'm going to go ahead and show you how to do this on the graphing calculator.
Okay, so we're going to do a quick little review of how to input and do operations with matrices in the graphing calculator. So the first thing is, where's the matrix menu? Well, the matrix menu is located obviously under the matrix key, which is if you hit the second key and this x to the -1 key, that'll take you to the matrix menu. Now some of you may have things already entered in the matrix menu, and you might have dimensions set up for some of your matrices. That's fine. When we do editing, we just type right over whatever's existing, so you don't have to clear anything out. And so we want to go ahead and go over to edit, and we're going to call our coefficient matrix that we just wrote A. So we're going to select A and edit it. So we need to establish the dimensions of the matrix, and it's a 3 by 3, 3 rows and 3 columns. So I'm going to go ahead and type this in. You can either type over the existing ones that are there, or if it's already a 3 by 3, you can just use the right arrow to move through into the matrix. So now we got to go ahead and put in our data. So when you enter data, like this first row, which is 1, 1, 1, as you press enter, it will move across the rows until that row is full, and then it'll drop down to the next row. So that next row was 9, 3, and 1, and then the final row was 16, 4, and 1. Okay, so now we need to exit that the matrix menu, so we hit second and the mode key, which is the quit, and we've got to get back into the matrix menu to set up the constant matrix. So we hit second and the matrix again. This time when we go over to edit, we're going to choose B, and we're going to set this up as a 3 by 1, 3 rows and 1 column. And this is where we'll put those constants of our 3 equations in our system. And they were -5, 5, and 16. So once again, we have to exit out of there. And now we're going to actually do the multiplication. So to solve a system using matrix multiplication, we have to multiply the inverse of A times B. So first we have to select A, so we hit the second and the matrix key again. And this time we're not going over to edit, we'll just stay right there on the names and just select A. And then we have to hit the inverse key, which is this x to the -1 key. And that's going to have the calculator go ahead and find the inverse of A for us. And then we'll multiply it by B. And there's B, we select B, press enter, and enter again. And there is our solution to that system, which also represents the A, the B, and the C of our standard form quadratic function. So if we were to substitute 2 in for A, -3 in for B, and -4 in for C in that general standard form, we would get the quadratic function that models those 3 ordered pairs that we were given.
so now that we know what A, B, and C are by solving that matrix equation, and A was 2, B was -3, and our C was -4, we can now go ahead and write our quadratic function by just substituting in what the values we got for A, B, and C. So our new function is going to be f of x is equal to 2x squared plus -3x plus -4, or another way to write that is 2x squared minus 3x minus 4. So that's our answer. Let's turn the page. So of course we're going to have a you-try question, and so we're going to go through that same process we just did with that last example. What you want to do is take your ordered pairs. I've got a new set of ordered pairs, 0, -3, 1, 0, 2, 1, and you're going to substitute each of those into ax squared plus bx plus c equals y, or f of x is equal to ax squared plus bx plus c, and create an equation from each one of the ordered pairs that you can then translate into a matrix equation and solve. So if you need any help with reminders, just turn back the page, take a look at the one we did together, rewatch the calculator tutorial if you need to. But when you're done and you've found the A, B, and C and written your quadratic function, you can tune back in and check your work. So go ahead and pause the video now and try the check yourself or the you try question. Okay, so I really want to thank you for trying that one, because there is quite a little bit of work to that question, and we'll just hope that there's not a lot of them on the practice set. But if you kind of figure out that process, each one is no different than the last. We just had to substitute our ordered pairs into the function, quadratic function, simplify, and create our matrix equation. So take a look at, if you didn't get those answers, check that, make sure that you had the right coefficients, that you had the correct signs, if there was any sign to be worried about, like for instance the -3, make sure that that was a -3 in your constant matrix. Be sure that you solved by using A inverse times B, but you should have gotten these values, this -1 for A, 4 for B, and -3 for C. So this is your final answer here. -x squared plus 4x minus 3 is the quadratic function that can be modeled using those points. Okay, let's turn the page. So as I mentioned earlier, back when we were studying linear functions, we did linear regressions, and we used the list function. We input data into the lists. We did the stat calculate linear regression, which wrote linear functions that modeled the data that we had entered. And we can do the exact same thing here, and we can apply a similar statistical method to make a quadratic model for a given data set using a quadratic regression. Now you also may remember that we used a measure of accuracy of our linear regression equation of R. And we said if the R value was really close to -1 or to +1, within like a tenth, that it was a really good fit. And so, but when we're talking about quadratic data, we actually want to use the coefficient of determination, which is called R squared. So it's not the correlation coefficient that we want to use the R, we want to use the R squared. A lot of you asked me about the R squared when we were doing linear regression, and I said, don't worry about that, we'll use that for quadratic functions. So the coefficient of determination, R squared, shows how well a quadratic function model fits the data. And the closer the R squared is to 1, the better the fit. In a model with an R squared of approximately 0.996, which is very close to 1, the quadratic model is a really good fit. Now, because R squared is a squared number, they're always going to be positive. So we're not going to get like a negative R and positive R like we did with linear regression. Our R squared will always be positive. So the closer it is to 1, the better it is. So here's an example where we're gonna apply that quadratic regression. A table shows the cost of circular plastic wading pools based on the pool's diameter. So you remember those little fun pools you used when you were a little kid, or the one you might have in your backyard for your dog, which is what I do. We want to find a quadratic model for the cost of the pool given its diameter. And we want to use the model to estimate the cost of a pool with a diameter of 8 feet. So notice the data shows me for 4 feet, 5 feet, 6 feet, 7 feet, but I don't know about 8 feet. So once I get my quadratic function, I could just substitute 8 in for my x, and that would estimate the cost for that 8 foot diameter pool. So I am going to create a calculator video again here that I'll insert here into the video, and it'll take us through the steps of this example. But you can always come back to your notes, and you can see that I have all the steps listed out. Step 1, entering the data into the list. Step 2, using the quadratic regression feature. Step 3, graphing the data and function to verify that the model fits the data. That may be a step that we may skip just because it involves having to do too much with our calculator, like putting on the stat plots and changing the window. But then inputting the equation and using the table feature to predict the output for an input of 8. And so I'm going to go ahead and cut now to the calculator video.
Okay, so in this video tutorial we are going to review how to enter data in the list so that we can do regression equations. In this case we're going to do a quadratic regression, but we've done this before with linear regression. Now the first thing we want to do is we want to make sure that our diagnostics are on. So when we're going to want to know what that r squared value is, which tells us how good a fit the quadratic function that we're going to write is to the data. And so we have to make sure that's on. And so whether it's on or not, it's the only way to really know for sure is to just turn it on. If it's on, it'll just stay on, and if it's not, it'll turn it on. So we have to hit the second key, and we're going to go down here to where the 0 is, and if we select that after the second key, then we're going to be in the catalog. So we can just scroll down in the catalog until we get to the diagnostics. And we want to go to diagnostics on. And there are the diagnostics, so we'll select diagnostics on. And then we have to execute that, so we hit enter again. And once it says done, that means it's actually turned the diagnostics on. So next what we need to do is enter this data. Now remember, we enter data under the stat menu, so we hit stat and we go to edit, and I've got my list here. My lists are all cleared out. If for some reason yours are not, what you want to do is push the up arrow so that you're on the title of your list and hit the clear key and enter. Okay. Remember, you never want to hit delete there because that'll delete your whole list. So if for some reason you don't have these two lists, what you would want to do is go to hit second memory and then reset your RAM. Then you'll have to go back through and turn the diagnostics back on. So if you're missing either L1 or L2, you're going to need to go ahead and reset the RAM. So you can do that by hitting the second and the memory key and then go down to reset and RAM. And then go back to second catalog and turn the diagnostics back on. So anyway, we've got our list. Now we're going to enter our data. So this was the plastic pool data, and we had 4 x values that were given, and they were 4, 5, 6, and 7. So we're going to enter our list for the x's, and then we're going to go over here to the list 2, and we're going to enter the data for the cost. And so the cost for that 4-foot one was $19.95. The next one was $20.25. And the third one was $25. And finally, $34.95. Now, if I wanted to graph this data, these data points, we would see that this, would resemble part of a parabola. In order to do that, we'd have to turn the stat plots on, we'd have to adjust the window, and there actually is a picture of it in your guided notes. So feel free to look at step 3 in your guided notes, and you'll see a graph of what this would look like, the data points. And that graphic in the guided notes actually shows when we put the equation for the quadratic in it too, so it's also got the curve running through it. But without the curve running through it, you just see those data points. That's what these would look like if we plotted them. But anyway, our most important thing is we want to get an equation out of this, a regression equation. So we're going to exit out of this, so I always just hit second and quit, but I think you can go straight to the stat calculate menu if you want to. So I hit stat and go over to calculate. Now this time we want to go down to quadratic regression, so that's number 5. We've done linear regression, we want to do quadratic if I went too far, and we're going to hit enter, and depending on whether you have the update or not, you might see this list. If you don't see this list, you just press enter again. If you do see this list, it's just giving you a checklist to make sure you've got the right lists associated with this regression function. And so we're just going to go down here to calculate and press enter, and there you go. So this gives us the A, the B, and the C for our quadratic function. All we have to do is just choose a place to round to. I'm going to round to 2 decimal places, and then we enter those values in for A, B, and C, and we'll get our quadratic function. So our quadratic function would look like this: y equals approximately 2.41 x squared minus 21.56 x plus 67.64. And that R value is 0.999808754. That's a really very strong indicator that this is a very good fit for our data, that this quadratic function does model this data very well.
So now that we've taken care of the calculator tutorial, we can take those values that we just found and we can write our quadratic model. So and we can actually see all this data right here on the page as well. So this is a graphic of what we just saw in the graphing calculator. And so the quadratic model is f of x is approximately equal. Now remember, we're approximating these, so it's a good idea to put the squiggly lines for approximately. 2.41 x squared minus 21.56, because that b was a negative number, and then plus 67.64. So I just decided to round to the nearest hundredth, and I just was consistent for all 3 terms, A, B, and C. So where x is the diameter in feet, and f of x is the cost in dollars of that pool. So for a diameter of 8 feet, the model estimates a cost of about, and this is what we found also in the video, $49.54. And again, we can see that right here also in our table. $49, and if we round it to 2 decimal places, 4 cents, $49.54. So let's turn the page. Well, that actually is going to do it for our lesson. I'm going to save this check for understanding for us to do to start the hour the next time we meet. So thanks for coming to class. We'll see you soon.